Now we're going to try a slightly different function. This is a rational function. For all of these functions, by the way, we have an applet for them. So if you want to play around with the applet now, or in the middle of the formula, in the middle of the problem, or at the end, do it whenever you like. So again, we want to find f prime using the limit definition, not using any shortcuts that we might know from some other place. So this is our definition. And again, I would say now take a second or a minute to try to figure out what the next line is, where the plus h is supposed to go. Pause the tape, make sure you get it in the right place before you watch me do it. So let's see, f of x plus h. Whatever we feed this function, it puts it down here and adds 4 to it. Meaning that if I feed it an x plus h, it's going to add 4 to it and then put that whole thing underneath a 3. And then minus f of x, minus 3 over x plus 4. And then this is all over h. So we definitely can't plug in the h yet because we'd be dividing by 0. So we know we're not allowed to do that. Plug in the 0 for h, I mean. So what have we got on the top? We've got one fraction minus another fraction. So what do we need to do to make that happen? Have to get a common denominator, right? So for example, if this were 3/5 minus 3/7, to get your new common denominator, you would multiply the two denominators together, 5 times 7. So that's what we're going to do here to get our new common denominator. We're going to multiply those two denominators together. And this will be one of many, many, many times this semester where we basically are multiplying by 1 in a clever way, because that's what getting a common denominator is. You're multiplying this fraction by x plus 4 on the top and the bottom, meaning you're multiplying by 1, but in a way that's going to make life easier for you. So I'm going to multiply that by x plus 4 on the top and the bottom. All right, so my new denominator is x plus h plus 4 times x plus 4. And this fraction I need to multiply on the bottom by x plus h plus 4, which means I also need to multiply by that on the top. And you've really got to be careful with your parentheses. And then I could write this whole thing still over h, but dividing by h is the same as multiplying by what? It's the same as multiplying by 1 over h. So I could put like times 1 over h over here, which would be the same as just putting an h down here, so that I don't have a fraction inside of a fraction anymore. But we still cannot let h go to 0 because we'd be dividing by 0 there, which isn't allowed. So we should multiply out the numerator in the hopes that, like in every one of these problems, things will cancel. So if I distribute that 3, I get a 3x plus 12. And we note that neither of those has an h in it, meaning that both of those are going to have to cancel. So there better be a negative 3x and a negative 12 coming down the line. Well, here we go. There's negative 3x. That's good news. Negative 3 times h gives us a negative 3h. And negative 3 times 4 gives us the negative 12 that we were looking for. Perfect. And I don't think ever in the history of calculus has it been a good idea to multiply out a denominator of a fraction. So you should just leave this the way it is. On exams and homework, I sometimes see people multiply out this denominator. It becomes messy, of course. They go through a lot of work. And then in the very last step, they factor it back out. And they end up with this very same thing. So save yourself the trouble of that. Don't multiply out denominators. X plus h plus 4, x plus 4 times h. And if we're lucky, everything should cancel that doesn't have an h in it. The 3x's cancel, the 12's cancel, and that's exactly what we want, right? So now we just have a minus 3h on the top. And on the bottom, we have x plus h plus 4, x plus 4 times h. So this is good, because we can cancel those h's. And now when h goes to 0, we're not going to be dividing by 0 in the denominator. So we just have to evaluate this limit. So we've just got a negative 3 on the top, x plus h plus 4, and x plus 4. So as h goes to 0, what happens to negative 3? Nothing. Negative 3 doesn't care what h is doing. As h goes to 0, what happens to x plus h plus 4? That h will go away. We'll just get x plus 4. And then as h goes to 0, what happens to x plus 4? Nothing. Doesn't care what h is doing. X plus 4. And then if you want to write that in a slightly more compact way, negative 3 over x plus 4 squared. And so that is our derivative. That will tell us the slope at any given point, any given x value that we want. So notice that the new thing about this problem was that we needed to get a common denominator, right? So anytime that you have a fraction like this, when you get to this step, you'll have to get a common denominator. Common denominator is one of those phrases that has escaped from mathematics into the real world and taken on a completely different and opposite meaning. For example, if you hear the police talking about a string of burglaries, and they say the common denominator is that in every case it occurred in a first floor apartment and the windows were unlocked and there was jewelry out on the dressing table. And the police say that's the common denominator. That's not the common denominator. That's the common factor. That's what everything has in common. The common denominator would somehow be putting together all of the things, whether they had anything similar or not, like whether they were on the first floor or the third floor, whether there was jewelry, whether it was a dog, doesn't matter. That would be the common denominator. But outside of a math classroom, everybody uses the word common denominator wrong. Try not to do that. All right, let's do a part B for this one. Now that we've got our derivative, let's find the equation of a tangent line. So in the previous example, we just found out where the tangent line had a slope of 0. Now let's actually find the equation of the tangent line at x equals 2. So I've got a graph over here, and this graph really came from stuff that we did on the very first night and on the second night. Because in the heart of our function 3 over x plus 4 is the function 1 over x. We know what the graph of 1 over x looks like. It basically has this shape. Multiplying by 3 stretches it vertically by a factor of 3. That doesn't really change the shape. And then putting the plus 4, remember from the first night, shifts the graph 4 units horizontally to the left. So the vertical asymptote that used to be at x equals 0 is now over here at x equals negative 4. So this is what the graph looks like. So I'm looking for the tangent line at x equals 2. So if we are trying to get what is a reasonable answer, what sort of slope should we expect for our tangent line? We should definitely expect a negative slope, right? This has got a negative slope. In fact, no matter where I draw a tangent line to this curve, I always get a negative slope. And you might look at the formula over here to convince yourself of why that is. If we want a tangent line, that means we want an equation of the form y equals mx plus b. So this is going back to the very first day. So which one can we find first, m or b? Back then we found m first. So m is the slope. So I want to find the slope right at x equals 2. You might say, that's hard because it's not a line. But now you know calculus, or at least you know a little bit of calculus. This formula here tells you the slope at any given x value. So m is f prime of 2. If I plug 2 into this, I will get the slope at this particular x value. And when I plug 2 into that, I get negative 3 over 6 squared, which is negative 112. So now we found our slope. So we know that y equals negative 1/12 x plus b. So what remains is to find b. So we need to plug in for x. We know we're going to plug in x equals 2, but we don't know the y value when x is 2, right? Do we know the y value there? We still have to figure that out. So when x equals 2, how do you find the y value of a function, of a curve? You go back to the original formula f of x here. When I plug 2 into this, that gives me the y value. So we plug into f prime to get the slope. We plug into f to get the y value. So 3 over 2 plus 4, which is 1/2. So now I know that the coordinates of this point here are 2, 1/2. So what can we do with that? Thus, I can plug in for y, 1/2. And for x, we're plugging in 2. So I think negative 1/12 times 2 is negative 1/6. If I move the 1/6 to the other side, it's like I'm taking 1/6 plus 3/6, which is 4/6, which is 2/3. Therefore, the equation of our tangent line is y equals negative 1/12 x plus 2/3. Let me just go over again this thing about finding b, because that's what people usually find to be most complicated about this problem. Sometimes people are tempted to plug 0 into the original function. If I plug 0 into the original function here, I get 3/4. So the y-intercept of the original function here is 3/4. But we can see from the graph that that is not the y-intercept we want, right? This number 3/4 is completely irrelevant to our problem, except in the sense that it tells us that our y-intercept should be less than 3/4, which we did get something less than 3/4, 2/3. This is the y-intercept we are looking for, which we figured out to be 2/3. And the way that we did that, again, we knew the slope, we knew the x value here was 2, but we didn't know the y value here. In order to find the y value 2, which we figured out to be 1/2, we plugged 2 into the original function f of x, and we got 1/2. And then we use that for our y value. So I hope this makes sense about how to find the equation of a tangent line. We'll do another example with a different function and a tangent line. But for now, you have the applet you can explore with this one. And you also have the applet for the upcoming function, which will be a square root function.